back for another lesson in Math 8. Today we are in Unit 3, Lesson 2, talking about solutions to linear equations. This is what we're going to really focus on, is what is a solution? What does it mean to be a solution to a linear equation with two variables in it? Very first thing we're going to start out with is talking about estimating area. When we look at these figures, we want to know which one has the largest shaded region. To accomplish this, we might think about looking at the white areas and say, this one looks like it's pretty big. But then I have two different triangles that look like they're a little bit maybe bigger or even equal to the same size. And then I have just this little section right here. So we could make a quick decision and just decide, or since we are estimating the area, what if I made these white areas just a little bit smaller? Then I took that out into two triangles. And what I see with that is this triangle right here looks an awful lot like the same size as this triangle right here. And I would estimate that this triangle and this triangle are probably the same as well. I would think, how can I make this next figure in part C also a triangle? So I'm going to go ahead and just connect that right there. And what I see is the triangle right here and the triangle right here, these three triangles all appear to be the same triangle. But then I look at this one right here and I see that's a much smaller triangle. I would say that the figure that has the largest shaded region is C. We're going to talk about apples and oranges when it comes to solutions to linear equations for this one. And so we're just going to go ahead and find out some costs. So at the corner market, the corner produce market, apples cost $1 each and oranges cost $2 each. So we have two different rates of change here, but not really in the way that you think that it will be. When we talk about finding the cost of 6 apples and 3 oranges, we can look at it like this. We could take 6 apples times $1 plus 3 oranges at $2 each. And we simply add together $6 plus 3 times 2 is 6. So we get a total of $12. If I take 4 apples, that's going to be 4 apples times $1 each plus 4 oranges at $2 each to equal, this is 4 plus 8 to equal, again, $12. Kind of cool. We talk about 5 apples, again at $1 each, plus 4 oranges at $2 each. So we have 5 and 8, which is a total of $13. Then we have a total of 8 apples. So 8 times 1 plus 2 oranges times 2, which is 8 plus 4. So we have, again, a total of $12. So you can see there's a lot of different ways in this one to get $12, but there's also ways to get more than $12. Possibly even less than $12. That's going to come back to us here in just a little bit. Keeping with this situation, talking about the apples and oranges, going on to number 2. Noah has $10 to spend at the produce market. Can he buy 7 apples and 2 oranges? Explain or show your reasoning. Given what we had before, if he has $10, then that $10 has to be equal to 7 apples at $1 a piece plus 2 oranges at $2 a piece. What we see is that $10 is really on the apples and oranges is 7 plus 4, which equals 11. Noah can't buy this. Nope, he's not able to. And the explanation is 7 apples and 2 oranges cost $11, not $10. So if Noah went and put an apple back, yeah, it would work. So what combinations of apples and oranges can Noah buy if he spends all of his $10? Well, I think that what we should consider with this is an equation. So when we talk about this, we know that the apples, each apple, let's say let X be number of apples and let Y be number of oranges. Now we'll go ahead and just make a table with this. Letter X and Y. Let's say that Noah buys 0 apples. That gives him $10 to buy some oranges, and oranges at $2 a piece would give him 5 oranges. Let's say he buys 1 apple. That leaves him with $9 And then we could consider this and say, well, let's see here. If it's $9, that would be 4.5 apples. Maybe not. But if he buys 2 apples, that's 10 minus 2 is 8, and 8 divided by 2 is 4 oranges. And then if he buys 3 apples, that's 10 minus 3, which makes 7, and then 7 divided by 2 is going to be 3.5. Well, that won't work either because we're not buying half an apple or half an orange, but I hope that what you can see here is we're developing a pattern. That pattern looks like this. If I go to my next number, as I increase my number of apples, I decrease in my number of oranges by 1/2. Or if I simply just go like this, 6, if I skip over one of these, I notice that my even numbers came out to nice even integers. This should be 2. 8 apples will give us 1 orange, and 10 apples will give us 0 oranges. So there's got to be a simpler way than just sitting there guessing and checking with a table. And that way to do it is use the 2 variables to write an equation that represents $10 combination of apples and oranges. Be sure to say what each variable means. Well, we did that right here. So we're going to talk about these variables. Let's say if I buy any number of apples, that's $1 for any apple. And then if I add on my oranges, we know the oranges, our number of oranges is Y, but our oranges cost $2 per orange. And then if I'm going to have any kind of $10 combination, it would be $10 for any number of apples for $1 plus $2 for any number of oranges. So then what are 3 combinations of apples and oranges that make your equation true? And what are 3 combinations of apples and oranges that make it false? Well, if I look up here to my table, I should be able to use any of these ones right up here that have integer values and be able to find those values. So 3 combinations, when I go to test this out, I can just substitute these values back into my equation. When I think about this, if I talk about 0 apples plus 5 oranges equals 10, we see that that is 0 plus 10 is equal to 10. So there's one of them. That ordered pair is 0, 5. And this is what we call a solution. We talk about this one down here, 1. Let's talk about the ordered pair 2 and 4. 2 apples plus 4 oranges. That would give me $2 in apples and $8 in oranges for a total of $10. So we know that that solution works as well. My third one, I should anticipate 4 and 3 would work. So 1 times 4 plus 2 times 3. That's $4 for apples, $6 for oranges is $10. So I know that my ordered pair 4 and 3 works as well. Now, how can I tell if there's something that is false? Let's just say on this one, let's say if I buy, well, think about back on our original parts right here. We're talking about $12. Let's use the ordered pair 1 and 2. If I say that I buy 1 apple and 2 oranges, what would that equal? Well, that would be 1 plus 4, which equals 5, not 10. That doesn't work for this situation because we're saying with $10. So 1 and 2 is false. What if I just said I wanted 3 apples and 5 oranges? Again, that one would be looking like this. $3 for apples, $10 for oranges. That would give us $13. So we can say that 3 and 5 is false as well because it's not equal to 10. Anytime that I do this to find out a false combination, my combination is supposed to equal to 10, not to anything else. So if it's not equal to 10, it's false. The next step here says graph the equation you wrote relating the number of apples and the number of oranges. What is the slope of the graph? What is the meaning of the slope in terms of the context? And then suppose that Noah has $20 to spend. Graph the equation describing this situation. What do you notice about the relationship between this graph and the earlier one? So if I want to go ahead and do this, we can just do a quick, simple graph. This will all be in the first quadrant because everything on this one has to be about positive values. And we would say number of apples here, and then the number of oranges. on the y-axis. Now, when we think about this, we could buy quite a few oranges for $20. I want to think with the end in mind right here to put them both on here. First off, I'm going to graph this equation, x plus 2y equals 10. But I also have to think about what happens when I get x plus 2y equals 20. And I have to consider the two of those equations as I want to build this graph because I'm supposed to compare them. So what I would think about here is the larger graph. If I could buy 20 oranges, or excuse me, $20 worth of oranges, that would be 10 oranges. So we'll see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then if I could buy apples, that would be 20 apples. And it looks like I went a little short. And now what I know about this is my graph is going to be big enough for both of these situations. When I talk about the first one, if I were to buy any number of apples, like here's a little strategy I want to teach you about. I want to think about the maximum number of apples that I can buy for the amount of money I have, and the maximum amount of oranges I can buy for the amount of money I have. And what's cool about that is that'll actually help me out with the data. When I talk about this, that means this. What if I buy 0 apples? 0 apples. Then I could buy 10 divided by 2 is 5. I could buy 5 oranges. So we could go 1, 2, 3, 4, 5. Put a point right there, and we find a y-intercept for this situation. What if I flip that around, and what if I say that I don't want to buy any oranges, 0 oranges for y? How many apples could I buy? Well, if I cover that up, it really doesn't exist. I could buy 10 apples. So right here. So that means on my x-axis, I could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I have two nice points here to be able to draw a graph, to graph a line that would tell me how many apples and how many oranges I could get at any point along here, keeping in mind that I can only buy whole numbers only. So what I'd have to be careful of is looking right here, where would these two lines intersect? And what I know about this, or what I notice, is that every 2 apples is the same as 1 orange. And so realistically, I'd want to just leave points like this. I wouldn't want to draw a line because you're only buying part of an apple, part of an orange. You don't really do that. So, but for the sake of understanding what we're doing with our lines, I'm going to go ahead and draw that in very lightly. When we talk about this or talk about the slope of this line, what we can do is a couple different things. We can either transform our equation into slope-intercept form, or we can look right here at our situation with the graph, and we can see that we rise -1 and run +2, rise -1, run +2, rise -1, run +2. We see that our slope of the graph is -1/2. Now, what exactly does that mean? Well, think about the change in y over the change in x. As we go down 1, we're talking about subtract 1 orange for every 2 apples that we buy. So when we talk about in terms of the slope, we can say if I subtract an orange, I get 2 more apples. But on the converse of that, or the flip side, I could say that if I add 1 more orange, I have to subtract 2 apples. So take away 1 orange, you gain 2 apples. Take away 2 apples, you gain 1 orange. Either way could be represented there. So let's talk about Noah's situation when he has $20 to spend. Graph that equation to the situation. What do you notice about the relationship between this graph and the earlier one? Well, let's go back to our first thought here and talk about this. What if I have 0 apples? 0 apples for x. How many oranges could I have? Well, I know that it's $2 per orange, and 20 divided by 2 would be 10. So I could have 10 oranges. So we can go ahead and graph that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as we talked about earlier. And then what if I took that onto the reverse of it and I said, what if I buy 0 oranges for y? And then we see that the x value has to be equal to 20. And so I come out here to the end of it where I counted out 20. And then what should we notice about these two graphs? Well, if I was a machine and doing this on graph paper, I would notice that those two lines are actually parallel. Because we didn't change anything about this situation right here in this expression x plus 2y, we didn't change the slope. I know this one has a slope of a minus 1/2 as well. All we changed was the outcome in that y-intercept. By changing the amount of money we had, we changed the amount of fruit that we had, but we didn't change anything about the costs. So the situation, what do you notice about the relationship between this graph and the earlier one? The slopes are exactly the same, and that made the two lines parallel. So same slopes means parallel graphs. Okay. Moving on to just something a little bit different. When we talk about this, I keep talking about these solutions, and I keep talking about what is a solution? What is a solution? What is a solution? Well, a solution to an equation is any pair of values, x and y, that make the equation true. So it has to be on that equation or on that line to make it true. In this case, you have two numbers. If you double the first number and add it to the second number, the sum is 10. Let's think about this. We're going to let x represent the first number and let y represent the second number. Write an equation showing the relationship between x and y and 10. So if you double the first number and add it to the second number, the sum is 10. Well, when doubling the first number, x is the first number, so we want to double the first number and then add that to the second number. Excuse me, the sum is 10. That looks an awful lot like what we worked on just a few minutes ago with our apples and oranges, only just a little bit reversed. So these wordings right here, this can be something that we really need to pay attention to be able to write an equation. So our next step is we're supposed to draw and label a set of x and y axes, plot at least 5 points on the coordinate plane, and then make the statement and your equation, or that make the statement and your equation true. What do you notice about the points you have plotted? So again, in this case, let's just go ahead and work with the first coordinate, but since this one doesn't have anything to restrict it, meaning that it's not like about apples and oranges, these data can go anywhere on the coordinate plane. There are no limitations to it. So let's think about how big I need to make my graph. Remember how we talked about with these pieces, talking about what would happen if x was 0 and y was 0? Let's go ahead and use that. And what we're doing is I'm actually teaching about something that's kind of like ahead of time. We're using what we call x and y intercepts. We already know about the y-intercept, but the x-intercept follows the same thing. When I take a 0 for the x, I'm finding the y-intercept because the y is the one that I need to figure out. So if x is 0, then in this case, y is 10. And that gives me a y-intercept. If I take the flip side of that, and I say if y is 0, right? All coordinates that have 0 for the y-coordinate give us the x-intercept, which would be 5 and 0 in this case. And so if I go ahead and graph these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I graph the y-intercept, and then I graph the x-intercept, I can actually come up with a line pretty easily. And if this was on graph paper, it'd be really easy to find a bunch of solutions that would make this true. So what we can do with this, plot at least 5 points on this coordinate plane that make the statement in your equation true. What do you notice about the points you've plotted? Well, I know that one of those points will be here. One of them will be here. One will be here. And one will be here. Now, how did I know that? Well, let's look at this. When we talked before, we talked about having values that would fit in, like this was like our apple and orange one. And so all I did is switch my x and y. What I kind of theorized with this is that if my slope before was a -1/2, and then I switched my x and y, I'm guessing that also switched my slope to its reciprocal value of -2/1. I want to double check and I want to see that. So I'm going to go ahead and work with those solutions like what we did right here. And I'm going to use those solutions, whoops, just getting there on this side, talking about these ones, I bet if I just switch those around, it will work for me. If I think about the ordered pair of 5 and 0, I started with that one, and I decrease my y by 2 and increase, actually I'm going to start here at 0, 10. If I decrease my value of x and my value of y, so we'll start with 0 and 10. Decrease my value of y by 2, I get 8. And if I decrease that value of 2, when we're talking about my y, if this is 8, if I subtract 8 from 10, start using some little bit of algebra here, eliminate that there, I get 2x is equal to 2. I can divide by 2 and divide by 2, and I find out x reduces to 1. So I have 1. Well, let's see what happens if I plug in 6 for y. If 6 is y, then I should have 2 for x. Let's see if that works out. 2 times 2 plus 6 equals 10. Well, we know that's true. That's 4 plus 6, so it's 10. We need to have 5 of these ordered pairs. Let's look at what happens here. That one is 2 and 6. This one is 3 and 1, 2, 3, 4. And then finally 4 and 2. And you'll see that that pattern holds true, and my prediction was accurate and correct for this situation, that my slope just really flipped over because I changed the coefficient of 2 to the coefficient of 1. So at least list 10 points that do not make the statement true. Well, what we need to know with that is points that make the statement false are just pick any ordered pair that's not on the graph. Remember that a solution to an equation, when we talk about that as a solution to an equation is any ordered pairs, 2 variables in the values x comma y that make the equation true. So all of these ones right here in my table, these ones are all true solutions because these are ordered pairs, points that are on the graph. And I could literally have an infinite number of those. But if I take another point that's like right here, that's in the vicinity, this is at 2 and 1, since that's not on the graph, that will make our equation false. And we can see that by going 2 times 2 plus 1 equals 10. No, that's 4 plus 1, that's 5. That's not equal to 10. If I picked one right over here, like if I did 6 or what if I just did one right here, 5 and 1? Well, 2 times 5 plus 1 equals, that's 10 plus 1, 11. That's not equal to 10. So that one doesn't work either. What we need to really recognize with this, with our ordered pairs, 2 and 1 doesn't work. 5 and 1 doesn't work. Using a different color, plot each point on the same coordinate plane. I could plot all kinds of points all over on this coordinate plane. And as long as these points are not on that graph, they are not solutions to this coordinate plane or to this equation. So what do you notice about these points compared to your first set of points? Solutions are on the graph line. Non-solutions are not on the graph line. All right. It's a pretty straightforward concept, I think, but if you have any questions, let me know. So to summarize, what we're after with this is we really need to pay attention to this concept right here, is that a solution to an equation, you've heard me say this now a couple times, is any pair of values, x and y, that make the equation true. We can think of the pairs of numbers that are solutions on an equation as points on the coordinate plane. And those points on the coordinate plane, such as this line right here, if we take those points anywhere on there, like what I said, these points, such as 1 and 3, will make our equation true. When we substitute those values of x and y into the known equation for the graph, we know that that has to be a true solution. All points that are not on the line are not solutions. So all points not on the line are not solutions. All points that are on the line are solutions. That's our major concept from this lesson. I hope that helps and makes sense. Please email me, check in with me if you have more questions. Don't forget to have a great day.